right? I'll just call it asynchronous sequential circuits. Okay, so let's consider a simple case here that I'm going to now design a NOR gate based circuit that will allow me to generate this non-overlapping clock. Okay, so let's look at how to do it. Okay, so now I have, let us say, an inverter here. Okay, I have a buffer here. Okay, I'm talking of a buffer now, and sorry, yes. Okay, so here what I'm basically saying is X and Y are inverted versions of each other, right? But they both can have the same delay. So let us say I'm saying this guy has a delay of 200 picoseconds. Okay, this is also 200 picoseconds. Okay, so one way to look at this, inverter is to actually take an XOR gate. Okay, take an XOR gate, and if you just tied this to 0 to logic 1 and gave an input A here, then you would effectively, this would serve as an inverter. But instead of this, if you tied it to 0, A would just go through unaffected. It's like a buffer, but the delay of both cases will be very similar. Okay, so you could think of using something like that to generate very similar delays for this particular case here. Okay, and then I am going to talk about the NOR gate, okay, which has another delay of, let's say, 100 picoseconds. Okay, that's what we had considered in this particular example. No, there also we said that was also 200, so I'll keep that also as 200 picoseconds. Okay, so I'm just saying, right, or just to make it different, maybe I'll make this 100 picoseconds just to sort of keep these two as different numbers for now. Okay, and what I am saying now is my phi 1 and phi 2 are essentially going to come out as non-overlapping clocks. Okay, so when you are going to analyze such a circuit, remember that the delay of these components is very critical. Okay, actually in the previous case, these synchronous sequential circuits and all, I could even analyze functionally with zero delay, right? I could assume that the gates introduce no delay, flip-flops have no setup or hold time or clock to Q delay, and yet I could do my analysis. Asynchronous sequential circuits will not work like that. You need to consider the delay of these small elements very accurately in order to understand the design and even analyze the design. Okay, I am not even talking about how to design this from scratch. I am talking about analyzing a given design, right? So what happens here is there are essentially two NOR gates, okay, N0, N1, and the output, if you remember the truth table of a NOR gate, right, is NOR 2, right? I have A, B and Y, 0, 0, 0, 1, 1, 0, 1, 1, right? It's going to be 1, 0, 0, 0. Only when both inputs are 0, will the output of the NOR gate even go high, right? So essentially this is what we are going to exploit, right, to ensure, okay, that the two outputs phi 1 and phi 2 can never be one at the same time, right? Why is that? You just look at it. Phi 1 actually takes phi 2 as an input, right? So the moment phi 2 goes high, phi 1's the NOR gate input to the n zeros input, one of them has gone high and therefore the output cannot go high anymore. It has to be 0, right? That's the essential thing that is going to be exploited in order to achieve this particular case here, okay? So I'll just move this to here so that I can draw these timing diagrams more usefully, more easily, I would say. Okay, so here it is. So let's start with my clock. I will draw this slightly more exaggerated. Okay, this is my clock and this is my x and this is my y. Okay, or I'll no, yeah, I'll keep x and y here. So this is my 0, okay. I'm going to keep this as it is, okay. And now what you observe here, right, is first of all, if any one of the inputs, right, to the NOR gate happen to be a high, right, then obviously the output will be a 0. Okay, so let's also keep that in mind. But before that, we can easily generate x and y independent of the NOR gates, because that's just a x is just an inverted version of the clock, right? So, but it will take some delay, right? So I'm going to draw it like this. Right, and y is going to be essentially sort of in sync, but it will be inverted. Okay, now I am going to focus on generating phi 1 and phi 2, right? So let us look at how we can start analyzing this. So phi 1, for example, initially x starts off at logic high, right? If x is at logic high, then the output phi 1 has to be low, right? It has to be low, right, until x. And what about now if, so now if phi 1 is low, right, and y is also low, then both inputs to n1 happen to be 0, 0, and therefore phi 2 has got to be high until this, at least until this point. Right, remember that we are, this delay here is how much? Is exactly 100 picoseconds. Okay, yeah, so phi 2 has to be high until this point. Now what is going to happen? My x drops to 0 and y goes high, right? Now the moment y goes high, obviously the output of n1 has to drop to a 0. That means phi 2 after 200 picoseconds will drop. Okay, now what happens to phi 1 in the meanwhile, right? So my phi 1 simply continues to be 0 because phi 2 is still 1. So therefore this will continue to be 1, okay. And then what happens is phi 2 has gone low, but for the output of phi 1 now, so what has happened is, if you look at the input to n0 at this time instant, x is 0, phi 1 is also phi 2 has also gone 0, but it will take another 200 picoseconds before phi 1 can go high, right. Therefore if you look at this, this will be another 200 picoseconds before phi 1 can go high here, okay. So this is what is going to happen. So my delay here, so this delay is 200 picoseconds and this delay is another 200 picoseconds, okay. So now what has happened? Phi 2 has gone low. So you see already that phi 2 has gone low and there is a non-overlapping period of 200 picoseconds which is controlled by the delay of n0, after which phi 1 will go high. That is the non-overlapping period that we have been able to control, okay. Now what happens? Phi 1 has gone high, okay. So let's look at this here. So now at this point, what we have is phi 1 has gone high, and at some point x will obviously go high and thereby cause my output phi 1 to fall below 0, right, after 200 picoseconds. So if you see, at some point x will go high. Remember, for phi 1 to go high, you needed both x and phi 2 to be 0, right. But now x has gone high and therefore phi 1 has to fall, right. It will fall, thereby causing the input of n1 to go to 0, and at the same time if you notice, y is also 0 and it will take another 200 picoseconds, right, for this to go high like this, right. So so this is going to be my output that's going to come out from phi 1, and phi 2 is also going to go high like that. And now let's see what happens to phi 2, right. So phi 2 has gone high, right, and at some point the input y will go high here, right, and then causing phi 2 to go low again after 200 picoseconds, and thereby you will get this kind of a thing. Then my again phi 1 will go high like this, right, and effectively what you see is that you can now get the delays and overlaps which are smaller than your clock that you are providing to this circuit, which was never possible in the sequential circuit, synchronous sequential circuit design that we looked at earlier, right. So that is the fundamental difference between the sequential and synchronous and asynchronous sequential circuit design, right. So this is just one of the examples, right. So by controlling the delay of n0 and n1, you can control this whole non-overlap period, right. And so this whole thing will simply continue exactly like this, right. It will just continue like this and then give you a very nice non-overlapping clock period generation, phi 1 and phi 2, okay. So this is a very simple example, and on a case by case basis you can analyze such things. But the problem with such circuits is you can have glitches that sort of cause the circuits to malfunction and all that. So you must be very careful about this. it is not generally it is advisable to work with sequential circuits because they are way more easy to design than I mean it's generally advisable to work with synchronous sequential circuits rather than asynchronous sequential circuits because they are way more robust and easier to design, right? So another application of asynchronous sequential circuits is when you have two uh, blocks operating at different clock frequencies and you want to send signals from one to the other. You will land up with setup and hold violations if you don't match, if these clocks are obviously different, right? And therefore you again capture these with these asynchronous circuits and then pass them on to the next synchronous circuit as well, right? uh, so with that, I'll really wind up the the discussion on the asynchronous sequential circuit design. And so note here, we are now talking, by the way, of delay of 200 picoseconds and stuff like that. And I could, for example, talk of a clock frequency which is, uh, you know, 1 gigahertz, 2 gigahertz, and I'll still be able to do all of this, right? Or 500 megahertz and stuff like that. I'll still be able to generate these non-overlapping clocks very easily. Maybe 2 gigahertz may be hard. It depends on the delay of these gates, but at least 500 megahertz and all that stuff I can easily do with this kind of a asynchronous sequential circuit design, right? So a final note, we have discussed a lot of these circuit design techniques, right? But I've really not named them for you, so I'll just complete this discussion with that. There are two types state machines. Okay, so you have one is called the Moore machine. Okay, and the other one, the uh, yeah. So I'll wind up this discussion on the sequential circuit design by just telling you, the two types of state machines that you'll encounter commonly. Okay, essentially you have two types of state machines. One is the Mealy machine. Okay, and the other is basically the Moore machine. So the difference really is, in how the output logic is actually controlled by the input signals. Okay, so if you look at the state machine, we are talking of a clock, right? This is our next state logic, right? D, Q, these are my inputs, okay, and my output logic is here, okay, output logic, and you get your, okay, outputs. So what is going to happen now is that if I have such a system, the output logic here is only a function of the states, right? These are my states, right? So this is basically the present state. So in fact, if you look at the the counter design that we did here, right? This would essentially represent a Moore machine because there is no input and the output is a function of the present state. So the output gets represented inside that state circle, right? On the other hand, what you could also have is the so this is basically what you call a Moore machine. Okay, and what is the advantage of this really? Because this output logic only responds to the present state, it is perfectly in sync with the clock. So something happens on the clock, the next state is then transferred to the output of the flop, and then the output logic just evaluates to some value, right? And therefore it's very easy to operate on that. You don't have to worry about setup, hold time, nothing, right? On the other hand, I could have another type of machine which is basically um, something very similar looking, uh, but this is what I'll call the Mealy machine, okay, where the input is now also a function of this thing. Okay, this is a, so the output logic is now a function of the input as well. Okay, so for example, you could consider I could consider the idea of a reset, right? Now the reset can be done in different ways, right? So you can have an asynchronous reset and a synchronous reset. The reset is, if it is done in a Moore machine way, then the reset will be done on the input next state logic, right, where you basically just make all the states 0 and then on the clock edge the 0 just comes at the output, right? But I could also simply take all the states, right, and it with a reset signal, which is the input signal, and just cause the output state to go to 0, right? Now if you did it in the latter way, where you put an AND gate at the output of the flip flop and just AND it with the reset, that becomes a Mealy machine, because the reset now can control the output of this logic directly, which means that any time the reset changes, the output can actually, the change in reset can affect the output and the state automatically, right? So that is something that you will encounter in future. So depending on whether you want to do something synchronously or asynchronously, you will have to deal with these different things. And for now I will just leave it at the Mealy machine. The state transition diagram will look typically like this. So you will go through states S1, S2 and so on, and you will have input, right? So you will have input 0 and output 1, right? And then here the input will be 1 and output could be 0, right? And from here you could again have 0, 1, okay, 1, 1, okay, something like this. So essentially the output value will have to be written outside the state circle, because it also depends on these input values, right? So the moment you look at a state diagram, you can easily say if it's a Mealy machine or a Moore machine and then determine if the outputs are going to be synchronous or asynchronous. So with that, I will wind up this discussion on synchronous and asynchronous sequential circuit design. Thank you.